In this lecture, that's chapter 7.2, we're going to extend our repertoire of elimination reactions to include alcohol substrates. We're also going to go back and have a quick recap of dehydrohalogenation reactions, especially those that lead to different regioselectivities. There will be 5 videos for this lecture. In video 1, we will extend the nomenclature of alkenes to include EZ stereoisomerism using Kahn, Ingold and Prelog rules. Video 2 is a recap of the E2 reaction and specifically the use of E2 to prepare an alkene from a primary or secondary alkyl halide substrate. The third video considers a variant of the E2 reaction called dehydration, and this is specific to primary alcohols. The fourth video considers the synthesis of alkenes from secondary and tertiary alcohols via E1, and the last video considers how carbocation rearrangements occur from secondary carbocation intermediates. Okay, so let's now take a look at the nomenclature. These are the Kahn, Ingold and Prelog rules for naming alkenes. So firstly, there is no specific relationship between cis and trans and E and Z, as they are both based on fundamentally different naming rules. The cis-trans style is based upon the longest chain, whereas the EZ style is based upon a set of priority rules. You need to know both styles. The EZ style is more reliable and is particularly suited to tri- or tetra-substituted alkenes, and especially when the substituents are not alkyl groups, as in this example. The Kahn, Ingold, Prelog priority rules are used for naming E or Z alkenes. Let's apply these rules to these examples now. First, what we need to do to each of these alkenes is to split them into two halves. So the top half and the bottom half, for argument's sake. The next thing to do is to look directly at the atoms attached to the sp2 hybridized carbon centers, and we look at their atomic numbers. In the first instance, both the bromine and the chlorine are assigned priority 1, and that is because both of these atoms on the bottom side of the alkene have the highest priority. The other two atoms, that's the carbon atoms that are part of the alkyl change on the top half of this alkene, would both be assigned priority 2. Now that then means we can make an assignment for this particular alkene. It's Z because both of the highest priority groups are on the same side, and the Z comes from the German word zusammen, which means together. When we look at the other example, the highest priority groups, this is still the bromine and the chlorine, are on the opposite side of the double bond, and this forms the E nomenclature. E comes from the German word entgegen, which means opposite. So what about if we have a tie between 3 atoms? What do we do then? In this case, we have 3 carbon atoms surrounding the alkene, which means that we wouldn't be able to make an assignment until we had prioritized based on a difference between those groups. Now the chlorine's automatically going to be priority 1 because chlorine has a higher atomic number than carbon does. So the next thing to do is to move outwards along those carbon chains until we have a point of difference. So this is very similar to what we do for when thinking about the assignment of priorities for the R and S nomenclature. So as we move down the top half, we would encounter another carbon atom, so it would be CHH. But for either of the methyl groups, the next atom down the chain is going to be a hydrogen. So therefore, both priorities 1 are on the top side, and then priorities 2 are on the bottom side. So this would be the Z alkene, and we would use the Z in front just like we do for R and S.
This concludes part A.
Initially, we're going to have a look at the stability of alkenes, as this will help us rationalize how certain alkene products are formed from either dehydrohalogenation or from dehydration reactions. But in organic chemistry, we don't generally spend much time discussing thermodynamics. However, these heats of hydrogenation provide a very useful rationale for the distribution of products seen in the reaction. So the more substituted the alkene is, then the lower the heat of hydrogenation, and this is a measure of how stable it is. Think of a ball being raised off the ground. The higher it is from the ground, the less stable it is. So for our but-2-ene, this is a di-substituted alkene, but here we can see a cis and trans arrangement. So for the trans arrangement, this places the two methyl groups on opposite sides of the double bond and are more stable. And the cis arrangement places them on the same side of the double bond, and that's less stable. Now, the mono-substituted, as seen by but-1-ene, that is even less stable. And this is really coming back to hyperconjugation. So the carbon-carbon sigma orbitals for the di-substituted would be able to donate some of their electron density into an empty carbon-carbon pi star orbital. And this is what provides the greater stability for di-substituted, tri-substituted, and the most stable tetra-substituted alkenes. As previously discussed in chapter 7.1, the use of a tertiary substrate in the presence of a strong but unhindered base leads to the formation of two products. These are constitutional isomers of one another. As mentioned on the last slide, the tri-substituted product is the more stable product of the two possible products, and this is also supported by the percent yields of these two isomers. Hopefully you remember the names of the two organic chemists that these types of products are named after. The first organic chemist is Zaitsev, and his rule says that the alkene formed in the greatest amount is the one that corresponds to the removal of a beta hydrogen from the beta carbon that has the fewest hydrogen substituents. The consequence of this is that the product formed will always be the more substituted one, and that the transition state of this reaction will be lower in energy as it's closer to the lowest energy product. Let's now compare the E2 reaction of a tertiary alkyl halide where there is more than one choice of beta hydrogen to be abstracted by a small unhindered base. Here we see the reaction of 2-bromo, 2-methyl butane with ethoxide, and there are two possible sets of protons to abstract, either those from the methyl groups or those from the ethyl group. When we look at this, the one that is going to give us the higher energy transition state will be either of the methyl groups, and this is because it resembles the less stable formation of that alkene product, i.e. the less substituted alkene. So this would produce 2-methyl, 1-butene, whereas if there is a proton abstracted from the ethyl group, i.e. one of those beta hydrogens, then this resembles a lower energy transition state, because when it forms the product is going to be more stable overall. And this is because we have here a tetra-substituted product, whereas in the previous example we end up with a mono-substituted product. Hofmann, unlike Zaitsev, didn't get a rule named after him. Technically, these products are really just non-Zaitsev products. However, as a result of Hofmann's study of reaction kinetics during a specific experiment, less substituted alkene products are named after him. Due to steric interactions, a bulky base such as potassium tert-butoxide cannot readily abstract the proton that would lead to the Zaitsev product. In these situations, a less sterically hindered proton is preferentially abstracted instead. This happens by a concerted E2 process. The reason the process is E2 is because of the use of a strong base. Had this been a weak base, weak nucleophile, then E1 would have occurred.
This concludes part B.
In this video we're going to discuss the E2 reaction of alcohols to produce an alkene. This slide provides a reminder about the leaving group ability of alcohols. Alcohols themselves are not good leaving groups as they are not stabilized bases. However, the conjugate base of the hydroxide group is water, and a protonated alcohol has a very weak base and a very low pKa of -1.7. So once the leaving group leaves, it forms a neutral molecule, and this is what allows the dehydration reactions to occur. Let's have a look at this in practice. At this stage, it might make sense to talk about the choice of acid in order to protonate the alcohol to make it a leaving group. So if you protonate it with a hydrohalic acid, these include HBr, HCl and HI, then it will convert the OH group to its conjugate acid, i.e. H2O+, which makes it a good leaving group. But instead of the expected elimination reaction, because remember the conjugate bases of these hydrohalic acids are weak bases, but they're fairly good nucleophiles, and so therefore this will allow either SN1 or SN2 depending on the substrate. And later on we'll be talking about rearrangements that can occur, especially those involving secondary alcohols. Now we know which acids that we don't use to effect elimination. Let's take a look at the acids that we will be using to bring about the elimination and the dehydration reaction specifically. Here is a specific dehydration reaction that occurs via E2, and this involves the use of a primary alcohol substrate. So a primary carbocation is too unstable to form a significant intermediate, and hence this is why this is an example of an E2, and that's a bimolecular pathway. So the first step would be the protonation, and note here that we're using sulfuric acid. So once we have protonated this, then a base here could either be water, it could either be the hydrogen sulfate anion, or some other weak Lewis base is perfectly able to remove or abstract that proton and produce the alkene product. What we don't want is a competing SN2 reaction, whereby if something is not only a weak base but also is potentially nucleophilic enough to kick out water. So this hopefully reduces that possibility by using a weak base, weak nucleophile, that is the conjugate base of our strong acid. To add some more detail to this, the reaction of the alcohol with a strong acid, likes either sulfuric acid or phosphoric acid, then is not an accidental choice, and this causes elimination rather than substitution. The alcohol is protonated and becomes a good leaving group. However, when we think about the conjugate base of sulfuric acid, this is hydrogen sulfate. It's a weak base, but more importantly than that, it's not a good nucleophile. The negative hydrogen sulfate anion is readily resonance stabilized. This means that it's not very nucleophilic, and so will favour the elimination mechanism over the substitution mechanism, and the same is true for phosphoric acid.
This concludes part C.
In this video we're going to focus on the E1 reaction that accompanies the dehydration of mainly secondary and tertiary alcohol substrates. The three main steps in an E1 dehydration reaction include the protonation of the alcohol, the dissociation of the leaving group, this would be water, and the formation of, hopefully, a stabilized carbocation, and the subsequent deprotonation of the beta hydrogen, thus yielding an alkene and an acid. Now, if we want to do E1, we do also need to be mindful of the acid that we use. Let's take a look at these now. So in answer to the question on the previous slide about whether we need to be mindful of the acid, the answer is yes. The alcohol is protonated and water leaves as expected. However, for the same reasons as mentioned in earlier videos, The hydrogen sulfate anion is not nucleophilic enough to attack the carbocation, and substitution is not the main product, elimination is. So let's now take a quick look at the bonds that are formed and broken. Well, a carbon-carbon pi bond forms, and a carbon OH group and a carbon-hydrogen bond are broken. There is also the formation of a hydrogen-oxygen bond in the molecule of water that forms as the byproduct. And these are the hallmark of an elimination reaction. If you look closely, you can see how a carbon-hydrogen bond on a carbon that is adjacent to the carbocation and a carbon-carbon pi bond forms in that position. These carbon hydrogens, their beta hydrogens, are ripe for abstraction. It's reasonable to propose that instead of attacking the carbocation to form a new substitution product, a weak base is just as capable of abstracting that proton that's adjacent to the carbocation, that's the beta hydrogen, and thus forming the alkene. An E1 reaction is a unimolecular reaction. This means that only the substrate is involved in the rate determining step. So this relies on the ability of the water molecule to leave. You might also remember that elimination reactions tend to follow Zaitsev's rule. We always form the most substituted alkene, or to put it another way, we remove a proton from the carbon with the fewest attached hydrogens, because alkene stability increases as we increase the number of attached carbons. So why the heat? Well, the heat generally tends to favour elimination reactions. We're also making more products than we started with. By no means is sulfuric acid the only acid that can help with this reaction. Phosphoric acid can be used as well. The tosic acid that you see on the right of this is para-toluene sulfonic acid, also tends to form elimination products. The tosic acid, however, makes the alcohol a better leaving group, and this is the subject of a later lecture. Let's now have a look at the reaction coordinate. It comes as no surprise that the formation of the transition state is affected by the stability of the carbocation intermediate that forms directly afterwards. Secondary and tertiary protonated alcohol substrates are capable of forming such a carbocation. We'll learn a little later that carbocation rearrangements usually accompany the formation of a secondary carbocation as a way of becoming more stabilized. This is the discussion of the last video. One thing is for certain though, there is no E1 with a primary protonated alcohol substrate. Let's have a quick look now at a secondary substrate just for completion. With a secondary alcohol, there are more products possible. However, secondary alcohols are interesting, and we're going to learn more about this in the next video. Here there is no branching of the carbon atoms to the left or to the right of that secondary alcohol substrate. So there are no rearrangements to worry about here, and the reaction would still proceed via an E1 mechanism and would produce Zaitsev's product as the major product with a trans stereochemistry. And yes, this would be via a secondary carbocation intermediate.
This concludes part D.
And in this video we're going to consider carbocation rearrangements, ring expansion and E1 mechanisms. So carbocation rearrangements typically happen with secondary alcohols, as this process is known as the 1,2 hydride shift said in the last video, and especially when there is more branching on one side of the alcohol than the other. So here we have a substrate that when treated with sulfuric acid, the water molecule leaves and forms this secondary carbocation. What happens next is a particularly fast step, as it has a stabilizing effect. By breaking a bond to the hydrogen on the more branched side of the secondary carbocation, the hydrogen shifts from this beta carbon and is placed directly onto the secondary carbocation. This process is known as the 1,2 hydride shift. Now this moves the positive charge to a more branched carbon. Thus, a tertiary carbocation is formed by doing this, and this is inherently more stable. Water can now deprotonate a hydrogen from any beta hydrogen that will yield the more stable Zaitsev's product. But is this the only shift that's possible? No, indeed it's not. Whole alkyl groups can be moved as well. These happen via the transition state that's shown on this slide, and when a methyl group is removed from the more branch side of a secondary carbocation, this results in a more stable tertiary carbocation. This type of shift is generally known as an alkenide shift, but for methyl groups specifically, this is called a methanide shift. The final example of carbocation rearrangement involves something called a ring expansion. This is always favoured, especially on going from a more strained ring like a cyclopropane or a cyclobutane to a ring with less strain. So for argument's sake, these would be typically 5 or 6 membered rings. The reaction begins as usual with the protonation of an alcohol group, typically a secondary one, and the water molecule leaves. What happens next is that the carbon 3-4 bond breaks and a new bond is formed between carbon 2 and carbon 4. This is known as a ring expansion. By doing this, the positive charge is now placed upon carbon number 3, which becomes a tertiary carbocation. And the last step proceeds as usual via the abstraction of the beta hydrogen on the more substituted carbon, thus yielding Zaitsev's product.
This concludes Part E.